Okay, we're live.
Here on planet Earth, we're in the midst of a global pandemic of epic proportion that has impacted the way we live and work to an extent we would have considered unimaginable just a year ago, except in Hollywood. And here in the San Francisco Bay Area, we're now also surrounded by fires to the north, south, east, and west. So we're doing our best to stay indoors away from the smoke and searing temperatures of an extended heat wave. But approximately 63 million miles away, traveling silently through the darkness and vacuum of interplanetary space, is a seemingly innocuous capsule-shaped object capped with a round disk of solar panels, hurtling along a trajectory at 40,000 kilometers an hour, designed to intersect Mars' orbit around the sun on February 18th, 2021, where it will deposit its payload. Inside that capsule is a six-wheeled SUV-sized rover called Perseverance, whose mission is to look for and possibly collect evidence of past or present life on Mars. Good evening, ladies and gentlemen, and welcome to the sixth installment of our now famous virtual SETI Talk series, which is the monthly lecture series produced by the SETI Institute in Mountain View, California. I'm Bill Diamond, the president and CEO of the SETI Institute. We're a 501c3 nonprofit research and education institution whose mission is to seek out intelligent life beyond Earth and understand and explain its nature, origins, and evolution. Like most of you, we're currently doing our work from home, but our research, education, and outreach programs continue even while the lights are out at our headquarters. Our SETI Talk series has been going on for many years, and we video record every talk, including tonight's presentation, and you can find all of our lectures and panel discussions on the Institute's YouTube channel, where we have more than 400 amazing videos on a wide range of space science topics waiting for you. I'd like to welcome all of you joining us live tonight on our Zoom channel. Also give a shout out to our friends and followers who are together with us this evening on Facebook and YouTube. And as we do at every talk, we like to poll the audience to find out who's joining us for the first time and who's a regular. So if you're with us on Zoom, you'll see a little pop-up on your screen where you can let us know. So select the answer that fits and hit the submit button, and we'll share the results with you in just a few moments. And now that we're virtual, we're able to engage a worldwide audience, and we love to know where you're watching from. So if you're on Zoom, use the chat function at the bottom of your screen and tell us where you are. And if you're watching on Facebook, use the comments section and give us your coordinates. We love to hear from you. And as you'll note in a moment, we'd especially love to hear from any of our friends watching from Australia, and you'll see why in just a sec. So tonight we're going to Mars, and we're joined by two of our own esteemed scientists at the SETI Institute to talk about the Mars 2020 mission and the Perseverance rover that launched from the Kennedy Space Center on July 30th, a scant 20 days ago. The conversation will be moderated by Dr. Adrian Brown, Deputy Program Scientist for the Mars Exploration Program at NASA headquarters, a native of Australia, there it is, and former research scientist at the SETI Institute. Dr. Brown will introduce our speakers and get us started on our expedition to the Red Planet. We'll have time for audience questions after the moderated discussion, and my colleague Rebecca McDonald will be fielding your questions on Zoom that you post using the Q&A function, again, at the bottom of your screen on the Zoom screen. We may not have time for all your questions, but we'll do our best, and we'll, of course, try and pick the most interesting and intriguing. So make sure your helmet is secure and your life support systems are fully operational. And with that, I'll turn the proceedings over to our expedition leader, Dr. Brown. Adrian, please lead us on.
Thanks very much, Bill. It's a great honor to be here helping out with the SETI Talks tonight. Just behind me here, you can see the Mars rover that is called Perseverance. This is the last image that was taken of that rover before it was packed off and launched back on July 30th. Thank goodness it was launched safely. And that was a major achievement in today's current challenging environment and COVID environment throughout the United States. So it's very appropriate that that rover is called Perseverance. And tonight, hopefully we won't need too much perseverance to get through tonight's action. But here to make sure that we get the latest in information, we're joined by Janice Bishop and Pablo Sobran. And first, Janice is both Pablo and Janice are scientists at SETI Institute who work on Mars and Mars rovers and Mars data. And Janice is a planetary scientist who explores using spectroscopy. She works on CRISM data for Mars and is especially interested in clays and what they can reveal about the climate and past climate of Mars. She is also interested in field work as well. She's done field work in Hawaii and all sorts of Mars-like environments as well. Hopefully we'll hear some more about that as we go into the discussions here. And Pablo is also a spectroscopist, but also an engineering and instrument guy. He is joining us tonight from St. Louis. And he is a Raman specialist, and we are going to hear about his adventures in Raman spectroscopy, I'm sure, since there are now 2 Raman spectrometers on Perseverance on their way to Mars as well. All right, so I am going to ask Janice to get us started with a little bit of discussion about how you have interacted with Mars over the past 30 years of your career and what you've learned and how you think Perseverance is going to help us.
Well, I'm happy to be here, and I think we're going to have a fun discussion about Mars tonight. And for those of you who are less familiar with the planet, Mars is one of our neighboring planets. It's a very cold and dry desert-like planet, and also has a lot of interesting outcrops that contain clays and sulfates and carbonates and other minerals that can tell us about the history. So the way we identify these is through remote sensing, and that's what I work on mostly, orbital remote sensing. And so we use this to try to characterize the surface and learn about the rocks in different places, and then use that to guide us in picking where to send the rover. So I'm going to show you a slide here. We'll see if this works. And this should, there we go. Let's see. So what I do is spectroscopy, and in order to learn about the minerals, we measure the bond length of the atoms in the crystal structure. So each mineral has different atoms and they're connected, and the way they stretch or bend, the vibrations of these bending modes and stretching modes have certain energies, and we can measure these with a spectrometer, and that tells us about the minerals and the rocks on Mars. And this works something like a guitar or piano. So those of you who are musicians will be able to understand this right away. So the pitch that you hear from a guitar or a piano varies depending on the length of the string. And it's the same thing for the minerals. So that bond length is related to, instead of the sound, it's related to the energy, which is related to the color or the wavelength that you can measure. So you can see in this diagram that I'm showing in the top left, we have the sun shining on the surface, and then we have a detector in our orbiter that's flying around the planet. So we're collecting pictures, images, like you would snapshots with your phone of the surface, looking from the orbiter, looking down. And instead of just 3 colors like our eyes see, we collect over 500 channels. So it's a big image, and part of the whole process is getting those sent back to Earth. But what we're doing then is analyzing all these channels, these 544 channels, and we're getting something with curvy, wavy lines like you see here on the top right. And we use these to fingerprint the minerals. So like each of us humans has an identifying fingerprint, each mineral has an identifying squiggly pattern. And we use that wiggly pattern in order to identify clays or sulfates or carbonates or olivine, different kinds of minerals. And then on the bottom, I want to just point out one last thing before we head on to Jezero Crater. When the CRISM spectrometer is flying, it's using a zoomed in mode with about 20 meters per pixel. And it can also run in a survey mode. So if you look in the lower right, you can see green and blue patches. And then if you look in the middle and the left of that, then you see zoomed out regions of the green and the blue. And so if you're averaging a large space, of course you get poorer resolution. And so we're using that for CRISM in order to see as close as we can on the surface. We're using about 20 meters, which is much better than we were able to do in the past. So when you think about Google view of your house, you can usually see a tree and a car and some other things. So when we're looking at Mars, think about 20 meters in each little data point, each little pixel in the view. And so in the past, in the recent past, maybe 15, 20 years ago, we were looking at things the size of a shopping mall and averaging that together. And so we've gone from looking at a shopping mall to looking at parts of your neighborhood. So maybe your house and your neighbor's house. And so when we're averaging that together, we get a better idea of what's present. And so we use this information about the minerals to tell us about water on the planet, and if it was acidic water or neutral water or alkaline water or low temperature or high temperature. And that can tell us about how the planet evolved and whether life might have been present. And so we take this orbital data and then we look at the whole planet at different locations. And then we use this in order to pick the landing sites. So, whoops, I'm trying to stop sharing here. So Jezero Crater is one place that has some really interesting minerals, and we'll be talking about that this evening and what they can tell us about Mars and potentially life there.
Thanks, Janice. Pablo, can you give us a little bit of an update on your work with your Raman spectroscopy and what and how that's going to feed into the mission for Mars 2020?
Yeah, of course, Adrian, and hi everybody. My work is similar to Janice's work. Actually, I joined SETI Institute back in the day thanks to Janice. So we've been working together for many
Adrian
years.
Too.
Yeah, it's a tight team here. But I'm more interested in the small scale side of the story. Like Janice just explained, she's looking from orbit, 20,000 feet view. I'm more into the microscopic view. Think about going down to the field with your magnifying lens and looking down at the microscopic features of the samples. So my work has taken me all over the world, examining and understanding special features of rocks in extreme environments like high deserts, the ice, North-South Pole, volcanoes, and acid rivers. And one of the things that we learned is how to build technology and how to launch that technology to Mars so that we can look for the same things elsewhere. So what this mission is all about, if I can find the screen I want to share, should be here somewhere here. Yeah, found it. So what this mission is all about, and hopefully you can see everything. It's not so much a mission that will be looking for life on Mars. It's a mission that is going to fetch or is going to catch the very best sample that we eventually will bring back to Earth to analyze in our laboratories. So where we are right now, as Bill indicated, is we're on the journey to Mars, but this journey, and we're almost 3 weeks in, is going to take us all the way into the 30s when we'll start launching a next wave of missions. And this time will be a mission that is combined NASA and European Space Agency that will bring a small rover that will find the cache left behind by 2020. And if everything goes okay, we'll launch it back into orbit where another mission will pick it and will bring it back to our labs on Earth. So think about this mission, Perseverance, as the very first of a wave of very persevering missions that will eventually allow us to get a sample from Mars back in our lab. And you've probably heard, if you're looking into what Mars is doing these days, you heard that Perseverance is a clone or a brother to Curiosity, and that is true, but only on the chassis, the structure of the mission. It has many differences, and one of them is that it has 23 cameras, and most of them are in color this time. So we're going to be able to get videos and images all over the rover in color for the first time, which will make for obviously very good posters for you to print, but also it's going to help the scientists find the best samples to work there. And my particular case, like Adrian noted, is concerned with Raman laser spectroscopy, and this time, for the first time, we'll fly in 2 instruments that have such a Raman laser, and one of them is mounted on the turret that you see here, and it's going to be able to scan the surface in a very fine detail, and hopefully find some of these organic compounds that you've heard are sometimes linked to life. So that's what we're thinking we might find with the help of these new instruments that we have in the rover. And I'm assuming we'll have a few questions on that, so I won't spend more time in this. But I'm going to point out to the top right corner that I guess the biggest novelty or the highest impact when it comes to public, as far as we know today, is that for the first time, a mission is going to fly on a controlled platform, in this case a helicopter, in order to test whether we can actually fly in other planets. This is a small camera that is going to be flying around the rover. It's going to be taking pictures not only of the rover, but also of the terrain ahead of the rover, so it can safely navigate. And just to finish this little intro, this is some of the data products that we expect to get back from the mission. And we have lasers that can shoot up to 10 meters away from the rover. And we have the lasers that can go in the arm, that can get the close-up. And the way to look at these pictures, and don't worry too much about the names, is that think about your cell phone camera. You take a picture of something. The cameras that we have on Mars are able to augment that reality that we're seeing with the camera, and it's able to tell us what the rocks are made of directly with one snapshot. So that's how we will start doing science early next year, by looking at images like this.
And that's the Pixel instrument, results from the Pixel instrument, right, Pablo?
That is correct. Yeah, that's the Pixel instrument. Yeah.
Okay. Thanks very much, Pablo. So I'm just, what I want to do first is bring up a poll question for the audience that we've prepared for you, because we're going to talk a lot about the possibility of finding life during this hour. So we want to just, if Lee could just bring up the poll question now. We're going to ask you to share your opinion on how long you think it will take NASA, or any other body for that matter, take humans, shall we say, to find life on Mars. 0 to 5 years, 6 to 10 years, 11 to 20 years, 21 to 50 years, or you have the opportunity to say we will never find life on Mars. So have a think about that question while we're going through our discussions, and we'll give you the results at the end of the talk. Okay, so Janice, I just wanted to go back to you. Lee, if we could move the poll down, please. Maybe. Janice, I'm going to just move that there. Okay, so Janice, you're mentioning the XRISM instrument, and it actually was the XRISM instrument, which was very shall we say, critical. It was a critical element in why Jezero Crater was actually chosen as the landing site for Mars 2020. Can you tell us a little bit about why that was and why the CRISM instrument was so critical?
Sure, yes. Well, the CRISM instrument provides us information about the mineralogy on Mars. And one of the things that we haven't seen too much yet at other landing sites was carbonates. And in particular, we were hoping to investigate carbonates that are in a lacustrine situation. So where we have sediments and valleys and fans. And so CRISM scientists have been using CRISM to map the minerals across the surface. And let me show actually a map if I can. Let's see if this works. Here we go. Oh, let's see. We'll do this one. So this is a map of minerals that have been mapped through orbital spectroscopy. And all of these different little colored symbols are different kinds of aqueous outcrops. So clays and sulfates and hydrated silica or chlorides. And then we've used these to guide where to place rovers. This is a map of Mars that I'm showing now. And you can see Phoenix is up north, Viking, Pathfinder, Opportunity, Perseverance is going to be here at Jezero Crater. And one of the reasons we picked Jezero was because of the carbonates and the other minerals that we see. And here's a nice sort of image zoomed in of an area near the landing site. And the different colors here relate to the different kinds of minerals that we hope to see. And so we've seen a few carbonates in other places, but the carbonates at Jezero Crater are part of this lake system, this paleo lake system. So they could provide the best evidence of stromatolites or some kind of early life if it did exist on Mars. So that's one of the reasons why it was selected. And then besides the mineralogy that we can see from CRISM, the other landing sites are much more recent. So Mars's timeline that when water was present on Mars was about 4 billion years ago or 3.5 billion years ago. And so this region where Jezero Crater is, these rocks are much older, about 4 billion years. And so we get a taste of some of the older rocks, which are probably different from some that we've already been looking at.
Okay. Janice, you mentioned the word stromatolite. Can you tell us a little bit more about that and what sort of mineralogy you might find associated with stromatolites?
Well, typically they're formed in sediments that contain carbonates. And so that was one of the reasons to look here, or sometimes also clays. So clays and carbonates together. And that's what we happen to see at Jezero Crater. So that's a good reason to go there. And on Earth, some of the earliest, some of the fossils of the earliest organisms are often stromatolites. They're some of the older ones. So about 3.5 billion years old. And so on Mars, the water was present on the planet about 4 billion years ago, up to possibly 3.8 or 3.5 billion years. And that's when the approximate dates we have from crater counting. And these aqueous outcrops that we are identifying through the mineralogy are about the same age or about the same timeline in terms of life originating on Earth. And so if Mars formed in a similar way back then it could be that life formed at about the same time on Mars. So going to an ancient site versus a more recent site would have a better chance of finding this. And so looking in the sediments inside the Paleo Lake, the carbonate bearing sediments may provide then a glimpse of these stromatolites, and potentially we could see them with some of the instruments on the rover, or we can identify sediments that look really likely and bring them back like Pablo was describing.
Okay. And just before we leave that, Janice, you mentioned Paleo Lake. How do we know that this is a paleo lake? And could you maybe bring up your previous
That
shot?
picture again? Okay.
Right.
Yeah.
You might have a hint for us.
So yeah, so looking at this, Mars has a lot of craters, and a lot of these craters filled up with water earlier in Mars's history, and we could see that from shorelines and from fluvial features. So places where water flowed in and flowed out, and in this case, this is the western part of Jezero crater, and water flowed in and brought debris with it and formed this nice sort of delta with fan deposits. And here, the interesting thing that we see from the remote sensing work from CRISM, some work Adrian's done and others, we see that the lower sediments have clays, where it's on this map, it says clay-rich delta and mafic volcanic floor. And then uphill a little bit where it's green, it says olivine carbonate basin fill. So the part of the sediments that are uphill a little bit have carbonates together with the sediments, and the sediments that are downhill in the Paleo Lake have just phyllosilicates. So we know it was a lot of the craters have evidence of water, but in this case we see a lot of sediments, so it was probably a lake for a much longer time than some of the other craters. And looking at these sediments, we don't really know from orbit how the minerals formed, if it was just material that was around the crater and just got pushed in as the water flowed, or if these minerals recrystallized in place inside the lake. And so that's something that Perseverance is for sure going to try to look at and analyze with all the tools on board and try to get a handle on.
Okay, so Pablo, that's an excellent point for Janice to hand over to you, because what would you be thinking about in terms of how the instruments, particularly the Raman instruments, but any other instruments on board the rover, could be used to find out what the aqueous or the water conditions, the water alteration conditions were back in 3.9 billion years ago?
Yeah, well, that's an excellent question, Adrian. And so the suite of instruments that are flying, they were very carefully selected to be able to work in synergy or in as a team, not so much as individual tools, but as one complementing the other. And so there are tools that we have that are going to be able to look underground. We have a radar that is able to send radar pulses under and be able to find perhaps layers of sediments that are covering other rock structures. Or even if we're lucky, we may find some reservoirs of water, if there's any over there. So by looking down, we're looking back in time. Think about Mars as although it looks dead and looks pretty boring, that's far from the truth. A lot of processes have been shaping the surface of Mars for the last few billion years, including losing the atmosphere and losing the oceans. And that's where we're going right now. We're going to the places that had water in the past. And now we're trying to find how much sediment got deposited on top of it. And so tools like the radar, then you have tools like SuperCam that can, this is the tool that can sap rocks at a distance from the turret. So you don't even have to drive anymore. You can just point and shoot up to 10 meters with the lasers, and you can very quickly find how much water do you have in the minerals. Of course, there's no water on the surface, but some of that water got trapped and got clustered in the mineral structures as it was leaving the planet. And we will be able to see, identify, and even quantify how much water got trapped into these minerals, which again is another clue that, combined with the radar, can tell us things about when and how much water did we have in the past at Jezero.
And okay, and so we've also mentioned a little bit about carbonate, and what sort of, I understand there's another Raman instrument on board as well that can look at organics. Can you tell us a little bit more about that? And could the carbonates that Janice introduced us to, could that be used to look at the carbonate rocks as well? And how effective could that be?
Yeah, so absolutely right, Adrian. the Raman instrument that is on the arm of the rover, the one that is going to be able to look very close up at the micron scale, actually, for these organics, is called Sherlock. And Sherlock has an ally on Mars that is called Watson. Surprise, surprise! And between the two of them, are going to be able to take very high resolution, high definition images of a sample of interest. And then once we have those, then we can shoot the laser. And if there is any organics, any of these carbon bonded compounds that we believe, or as far as we know, are life depends on them. Life is based in carbon, as far as we know from Earth. So this instrument will be able to find those carbon molecules that sometimes can be associated with life, sometimes not, like for example with carbonates. So we'll be able to distinguish between them, thankfully. So once we find a rock that is carbon based, like carbonate, we'll know. If we see some of these aromatic molecules, some organic compounds that like amino acids, lipids, fatty acids, alcohols, perhaps, we'll be able to see those as well with Sherlock. Yeah.
And you mentioned that is on the arm, so that will also be used as part of the sample, the sampling drill as well, right? So the Raman would be used on those samples before drilling a sample, I think. Is that right?
That's absolutely right. So I think that we spent the last 10 years building this mission. Most likely we'll spend the next 10 years operating the mission on Mars. And we will, if we're lucky, we will get 20 samples captured. So it's been a lot of effort, and it's going to be a very hard choice to make what samples to get. But the team is committed to do all the work that is necessary, analyze everything that we can before we pull the trigger on getting a sample. And part of the reason why we're doing that is because we have never to date have a mission that can drill down to 4 or 5 inches, like this core is going to be able to go, and get that sample intact, getting this core that it will preserve those structures, maybe even stromatolites, like Dennis described earlier. For the first time, we're going to be able to do that. And as you know, when you do something for the first time, there is certain risks and certain feelings that maybe things can break or not work as expected. So obviously the engineering team building the drill has worked hard. It's not the hardest of the mission to make sure it doesn't happen, but because of every sample is so precious and so difficult to get, before we decide any of that, we spend a lot of time, weeks, if not months, analyzing that particular area with everything we have, including obviously the instruments that are on the arm, on the turret. Yeah.
Thanks, Pablo. And so that process of selection of these samples, it would really go back years and years to our own work here on Earth analogs of Mars. That I think, Janice, you are an expert in Mars analogs here on Earth. Can you tell us a little bit about how your work on the analogs could feed into the job that Mars 2020 is going to be doing?
Sure, I think you're right. In order to best understand any of the sites we're looking at on Mars, once we're there, time is critical, and we want to understand the data as soon as possible. So there's been a lot of Mars analog work at various sites to try to help prepare the team to be ready to understand that data. And so a lot of the places I go to are volcanic islands, and my background here is from one of those sites. that looks a little bit Mars-like, but there are a lot of volcanic places where the surface is very windy and dry and altered, kind of like Mars. But if you look below the surface, then you see a little bit more diversity in the mineralogy. And so what we often do in the field is dig a soil pit and look at the stratigraphy. And another place we do that is in the Antarctic dry valleys. And there it's very dry like Mars. And so any water on the surface would just dissolve immediately and vaporize during most of the year. And so when the glaciers melt, you don't see a lot of liquid water sticking around, occasionally in the summer. But instead of water on the surface, though, there's water below the surface. So there are salts, there are chlorine salts and sulfates below the surface that seem to be soaking up that water. And so we may see this on Mars as well. The surface is very dry, and we're not sure how far down you have to go and exactly which locations, but we have seen evidence of ice below the surface on Mars. So the radar that Pablo talked about is going to help us figure out what's below the surface, and whether or not there's water ice, there will be interesting minerals. So when we're probing the sediments, we want to know what's on the surface, but also what's below that and a little protected. So on Mars, the whole surface is sandblasted continually by dust storms. And so there's a lot of dust covering the surface, and all of the missions have found coatings on the rocks and dust layers. So if we can dig through that a little bit, we can see the sediments, the historical deposition perhaps of how the sediments were laid down. So hopefully we'll be able to see that. It's going to be a small sample too, but still it'll be, you know, a few centimeters. So that'll be helpful. I think that'll tell us a lot. And it could be that a lot of scientists are studying analog sites already, but as we look at Jezero and as we start getting more answers in the mission to what's there, I'm sure people will think of other ideas of, oh, my favorite place over here, this, and there'll be a lot more analog sites popping up that people are going to go investigate to try to understand this site.
Mm-hmm. Thanks, Janice. So Pablo, how about, could you tell us a little bit about the analogs on Earth that you like to use in your work, and how you think they might be giving you more information about what Mars 2020 might find?
Yeah, of course. Very much like Janice, I've been lucky enough to be able to work in places like what she's showing in the background. And so, but I took a different approach to those analogs. And in my case, my thinking always was, well, if you have a mission on Mars and something breaks, that's game over, right? You cannot call a technician to go fix it. There is no AAA that is gonna tow you and get you new wheels. You basically, you're stuck there, right? So the work that I've been doing in these analogs over the last almost 20 years, it's been towards challenging the technology, basically breaking things, learning why they break, and then going back to the lab and fix them and make sure they don't break again. And as you can imagine, it's much cheaper to do that kind of work here on Earth. Flying is expensive, and it probably will become more expensive as we go out of pandemic. But going to Mars, it's a whole different business. So the idea here is that we use these places, like Janice was describing, places that are extra dry, places that are extra cold or extra hot, places that have a very corrosive environments that will harm your piece of machine. So we use those as a proxy for what's waiting for us on Mars. So we basically prepare our machines, our tools, our instruments to survive there. But not only survive, actually, we teach them, we teach ourselves how to build them so that they operate in an optimal way once we are out there on Mars. Okay.
And Pablo, you, in fact, one of the instruments that you built was to look at a borehole with Raman instrumentation. Is that correct? Can you tell us a little bit quickly about that and how cool that was?
Oh yeah, thanks for asking that, Adrian. That's one of my favorites. So as Janice is explaining earlier, Mars atmosphere is pretty harsh environment. So as soon as you bring samples out, things will start to happen. If there is water, water will go away. If there is some organic species, it will get fried, perhaps with the UV radiation. So things dynamically change very quickly. So sometimes before you even have the time to analyze it, the things that you were looking for are gone. So we started tinkering with the idea of instead of bringing a sample to a rover or to Earth, why don't we bring an instrument to the sample? And because the samples of interest are deep, not deep below, but they're under the surface, as Janice explains, we need to bring instruments down there. So there is a whole team of companies and universities and NASA in the country that we've been working together into miniaturizing our sensors. The ones that you saw in the slide that are the size of basically a microwave oven. We're trying to make them small enough to fit in a small drill bit. The drill bit that you use to poke holes in your wall to hang your things, that's the level of shrinking that we're doing these days. So we were able to test a number of times this in different places and be able to, for the very first time on Earth, do a chemical profiling or mineral profiling of what's under our feet by looking at bringing these instruments down there. And the Atacama Desert, one of our favorite places in Chile, being high desert, probably the driest place on Earth, it's been our playground where we've been able to test this for the very first time. So it's very exciting times, Adrian, for this. And we're hoping that in the next missions, we'll start seeing more of these subsurface instruments. And I'm going to finish that to say that we're not the first ones doing this. The European Space Agency is launching the ExoMars rover 2 years from now. And that rover will have a drill bit that is going to be able to go down 2 meters, so 6 feet down. And it will have an infrared spectrometer, very much like the one that Janice was showing earlier, CRISIM, that takes this amazing maps of mineralogy. It'll have the ability to do that underground as well. So that's the future of the missions that way. Yep.
Great, thanks. That's fascinating, Pablo. So I think we're going to go to some audience questions now. So I will hand it over to Frank Monchi in the command center for some audience questions for Janice and Pablo.
Actually, I'm going to get the first question for you, but that's okay. Frank and I are going to go back and forth, so he'll be on in a moment. And the first question is about Ingenuity. People love Ingenuity, and Daniel is interested to know, what is the range of Ingenuity, in that how far can Ingenuity fly?
Pablo?
Great question. And the answer is we don't know exactly, but here is what we're hoping for. And I'm gonna just go very on why now. So to be able to fly, we need to push against the atmosphere. That's how helicopters fly on Earth. That's how your toy drone or your commercial drone on Earth works. So the problem is that Mars only has about 1% of the atmosphere that we have on Earth. So to be able to lift and move on Mars, you need to spin your propeller much faster than you would do on Earth. And also your wings, your wingspan has to be much larger than on Earth. So because of that, we have not been able to do it to date, and we hope to be doing it next year. The problem that brings into building the instrument is that you need to spend all the mass that you can fly, you have to spend it in battery. So basically the helicopter is a flying battery with a camera that is not better than the camera that you have in your cell phone. So the camera weighs 20 grams, and that's a few ounces. And the helicopter weighs about 2 or 3 kilograms total. So but because of this, the answer that I'm going to give you is probably going to sound pretty 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 bummer. But it's perhaps if we can do flights of 20 to 30 meters without having to touch down and wait for the sun to recharge the batteries, then that would be lucky. So I would say, Adrian, I think you probably have maybe some of that on this, but I think 20, 30 meters is about feasible range, like a basketball court, basically. Range.
Yeah, from what I understand, they are going to conduct 1 to 5 flights and try to get further every time they try something. So everyone will be a little bit more advanced than the last in terms of what they're going to be trying. And yeah, it probably will be 20 meters. But if they can go further, then I think on flight 5 or whatever is their final flight, they might try a fairly long flight.
Yeah, that'll be the last flight, and then bye-bye, right?
Yeah.
So I think so one of the things that the helicopter is going to be doing is not only taking pictures of what's ahead of the rover, but also pictures of the rover itself. So I would encourage everybody here and tell your friends and family to stay tuned, because I think those images are going to be something that obviously we haven't seen before, and it's going to be an opportunity for us to see Mars from a very different perspective than what we're used to. So it's very exciting for everybody, I think.
And I want to jump in and say that even if Ingenuity can only travel 20 to 30 meters, still it's a view from the top. And so up to now, every rover has only seen at ground level whatever is in front of it. And so as a field geologist, you want to go to the hill, the highest hill you can find, look around. Or if you travel with Pablo in the field, then you can take a drone and get pictures. Either way, if you can see from above, it gives you a huge advantage in terms of where to go next. So when you're measuring a rock and you want to just get a quick aerial view of how similar is this to the other stuff, and help you make your decision in terms of, should I measure another rock next to this, or should I keep going and measure something a little further away or behind me that you might not be able to see.
Yes.
All right. So we have 2 questions here which are kind of similar, one from Olga and one from Suresh. They want us to clarify the main discriminating features which could be detected by Perseverance to decide whether or not we have found stromatolites or just non-biological created rock. So basically, how do you identify stromatolite?
Janice, did you want to talk about that?
All right, I'll talk about that a bit. So we're going to be looking at images, so that one of the things the Mastcam Z instrument can zoom in, I think that's the Z part, and then zoom out. And so when we're looking at samples, we'll be able to look up close, kind of like an SEM, a scanning electron microscope that we use in the lab to look at mineral grains up close. And then we'll be looking at the chemistry as well, the elements. So looking at the morphology, the shapes of the grains, and then the chemistry in terms of organics, and then the mineralogy and the chemistry, and putting all that together. And if there are or were life forms, then they would have needed an energy source. And so sometimes you see a disconnect in terms of the kinds of chemistry there, and also mineral assemblages that you wouldn't normally find together. So all of those are clues to the picture. And I think the morphology will be one of the first clues to look at. But you're right, in the whole, a couple decades ago, we had a big story about the Martian meteorite, the ALH 84001, where people thought the shapes looked like bacterial fossils. So shapes can mean a lot of things, and each person might have a different interpretation. So we'll be using the shapes that we see, the morphologies, together with organics and other chemistry and mineralogy to try to understand that. And then, of course, if it looks really juicy and interesting, then we'll pack that in one of those little cache containers and hopefully get it fetched back to Earth.
Thanks, Janice.
Yeah, thank you. I think this is a question for Janice as well, from Aaron. Are there minerals on Mars, or do we know if there are minerals on Mars that aren't found here on Earth?
There is one, and it's called Meridianite, and it was named after Meridiani Planum, which is a big area on Mars where the Opportunity rover was. And this mineral was discovered by a Canadian scientist in a very cold place. He was studying, it's a hydrated sulfate mineral, and he brought some hydrated sulfates home to his garage to study over Christmas vacation. And it got super cold. It was one of the coldest winters ever. And this formed a new mineral. And when he was analyzing this, and as he was working on it, he reported what he was finding. And the scientists at that time studying Meridiani Planum with Opportunity were getting all excited because what he was finding was similar to some of the things they were finding. So it was named after Meridiani, but there aren't a lot. So there are a couple other, there's some other sulfates that have some really interesting properties that aren't stable here. And I've done some heating experiments in the lab to dry out certain kinds of sulfates. And we get those spectral features for a very short time, a few minutes, maybe half an hour, and then they're gone because it's really hard to contain it in that environment on Earth. So we don't have a name for that other, and I'm not sure it's a mineral, but Meridianite is a mineral and needs very cold conditions.
Good. So we have a question, some very interesting here. What are the chances of finding living organisms, not only evidence of past life, using this mission? And this is a question from Jorge Arturo.
Pablo, do you want to have a go at that one?
Oh, yeah. So I'm gonna say low, but I'm speaking from myself here, not on behalf of NASA or the mission. So and here's the reason. So to be able to do the amazing science that we're doing in space, and this is not just for Mars, but applies to every single mission out there, you have to make compromises. You cannot launch and send the best lab that you have on Earth out to space to do the best science you could in the lab. That's not a possibility. You need to start cutting corners, so to speak, trading performance for energy consumption or for mass and volume, or even worse, for survival. So you need to shield it sometimes with the materials to be able to operate. So what it comes to is that we are not sending the best technology we have to Mars on this mission. We're sending the best technology we can build today that will do the best job we can on Mars, that is going to help us understand a bit more about the potential for life on Mars. The decision was taken some time ago that we have the highest probability of finding life on Mars if we bring a sample back to Earth, where we can put the best labs and the best minds to work on the problem, as opposed to a robot on Mars. So considering all this, it becomes pretty clear that we're not looking for life with this mission. That's not a mission goal. So the chances are not high. Again, not because we don't want to, it's because we don't think we can. So instead of the question being, what are the chances that we find living organisms on Mars with this mission, the question should be phrased as, what are the chances that we can select high value or jackpot samples, if you want, that can tell us whether there is living organisms on Mars, but that's going to happen on Earth.
Excellent. The next question comes from Azul. What parameters will Perseverance measure to help design an optimal future human mission to Mars?
Want to try that one?
Oh, yeah. So there is an instrument that we haven't mentioned yet. It's called MOXIE. So there is an instrument there that is going to be sniffing, or I guess inhaling CO2 from the atmosphere. It is going to process the CO2. It's going to split the carbon and get the oxygen. And it's going to demonstrate that we can actually generate oxygen for humans to breathe from Mars resources. So the name of the game here is that if we are to have permanent settlements on Mars or the moon, for that matter, we cannot bring every resource with us from Earth. We have to mine those planets for resources. And in the case of Mars, a critical thing that we can get is oxygen. So this MOXIE instrument is a technology demonstration that is going to prove that we can obtain X amount of oxygen from Y amount of CO2. So stay tuned for that ratio. I think it will be really or revealed, I guess, as soon as the mission starts working, how efficient that process is.
And the oxygen will also be useful for rocket fuel as well.
Oh, absolutely, yeah, absolutely, yeah.
So I'm putting together two questions from Ricky and Dharmesh. They want to know more about the mission, the return to Earth segment of the mission. Is it funded? Do you know if NASA has contracted already companies or institutions to do the analysis? And how long it will take for the samples to get back to Earth to be analyzed?
Can I just can I answer that question, because I have one slide to show that I think will hit this question. Is that okay? So
Go for it.
can everyone see this? This was part of a presentation that was given by Jim Watson earlier in the year on 9th of March regarding the Mars sample return campaign. The current head of science at NASA, Thomas Zurbuchen, is a very big advocate of Mars sample return. He is taking it on board as something that he wants to make sure is bedded down into the architecture of the planetary science side of his science mission directorate. So he's actually Jim Watson commissioned JPL to work out a plan for what would be required for these samples to be returned and when they could be done. For those of you who are not familiar, we have to wait every 18 months or so, or 20 months or so for Mars to come into a favorable opposition close to us. And so there are some very good oppositions coming up in 2026 where we would want to send our first sample retrieval lander at that time. So that's, being only 6 years away, that's amazingly close. So this wouldn't, as a result, this wouldn't do any science on Mars, but it would just go put a little small rover that would run up to Mars 2020, or if Mars 2020 wasn't there, it would just collect some of those cached samples that we've been talking about. Then it would go back to the rover would go back to the launcher. The launcher would go up to the Mars orbit, and then it would go up to the other element, which is the Earth return orbiter. And that Earth return orbiter would then take the samples back to Earth, and then they would be dropped into Utah or somewhere similar. And that would happen in 2031. So that time schedule is there at the moment. And hopefully it doesn't slip, because it costs a lot of money when these things slip. So we think that this is a possible candidate and the most probable candidate for the sample return mission to take place.
Okay. Oh, sorry, you go, Janice.
I was just going to show a graphic about the sample caching while we're thinking about the next question. So if we look here, this, whoops, something weird happened here. Okay, can everybody see hopefully there's a rover and you can see it chasing around. Okay, so this is the idea when we're talking about caching. The rover's going to leave these samples, maybe not everything in one place, because there's a fear that what if somehow the retrieval rover can't get there. So in any case, these caches with the samples will be deposited. And then what Adrian was talking about, then the next small rover will come and retrieve those from this kind of a location.
And of course, there's no GPS on Mars.
Yeah.
So, so maybe that's for a different talk. But you know, if we wait too much, Adrian, there may be too much dust on top of them, and we may not be able to see them. So that's another factor here.
Indeed.
Okay, I'm being told this is the last question. And the question is this. It's from Daniel. If Perseverance does detect biosignatures preserved in Jezero crater carbonates, what happens next? Is there a plan?
We'll let Janice go first, and then maybe Pablo.
I don't know if there is a plan yet, but I think that there's definitely been a lot of thinking over the last couple decades about sample return and how we're going to archive that, so that if we do find a really juicy sample that looks like it has stromatolites, for sure we're going to capture, you know, 2 or 3 or 4, you know, several of those. And when they come back, it'll probably be quarantined. So when the first samples came back from the moon, even though we now know the moon is so desolate, we didn't know at the time. So when the first samples come back from Mars, especially if they look like they might have life, nobody's going to touch those right away. They're going to be locked down in quarantine and very carefully examined in order to make sure that nothing dangerous gets out that could possibly spread. So, and then I think the process will be, scientists can write proposals and request pieces of the different samples to do analyses, but these are going to be tiny samples, and probably some of the studies are going to have to be there at this special sample facility, and potentially down the road, some of those samples could be taken to other facilities.
Pablo?
Yeah, I think I'm gonna give it more of a philosophical angle here, and it's,
Perfect.
you know, claiming that we found biosignature, like no question about it, that's a big claim. And to be able to do that, we need to find multiple lines of evidence that is the case before we can go to the press and you know, get a cover page with the big news. So the mission as it is now does have enough guns if you want to really do that multiple evidencing. And the plan is, as Janice say, if this multiple evidencing is true, which again, it'll take a lot of time to make sure everybody validates that and everybody's happy with that. The plan is bring the sample back and bring 3 or 4 others nearby just in case, right? So that's the plan. And then the rest is future.
Yes, indeed. The future is going to be very, very fascinating with as far as this rover goes. If I think before we shoot across to Bill, if we could just have a quick look at the poll results, so that we could, Lee, if you could possibly bring out the poll results so we can get an idea of how many people voted. So that it looks like we have 32% of you said that 6 to 10 years we would know that it should be, whether there is going to be life on Mars or not. That's good. Even more reassuring perhaps is that only 11% said we won't find life on Mars. So that's good. That's probably just a reflection of who we've got on our audience. But yes, hopefully those percentages will move a little bit over the next couple of days as you think about and rewatch tonight's episode, as I'm sure you will. But I'll throw it back to Bill now to send us off.
Great. Well, thank you, Adrian, and thank you, Pablo and Janice. That was absolutely terrific and fascinating. The last question was interesting on a couple of levels. First, because this issue of that Pablo was raising about whether, you know, there's an indication, you know, a biosignature would be indicative, but not necessarily definitive evidence of life. And this is one of the interesting things about SETI as an endeavor, or looking for techno signatures, looking for radio or optical signals that we can definitely and sort of absolutely differentiate from natural phenomena. You know, if we get such a signal and can validate that it's not from a local source, i.e. an Earth-based source, that becomes a more definitive bit of evidence for intelligent life beyond Earth. And so for that reason, you know, we always think, of course, especially here at the SETI Institute, that technosignatures searches are such an important and relevant part of the broader search for life beyond Earth. But needless to say, the search for life on Mars, past or present, is just a fascinating and of course, technologically marvelous undertaking. And we're all hoping that, you know, those lower number of years estimates on the pole were correct. The other interesting part that was brought up, and Janice covered this, is the issue of planetary protection. And so those of you who are regular followers of the Institute may have seen the press release we announced a few weeks back, where we received the contract from NASA to lead essentially their efforts at planetary protection, which is really all about preventing both forward contamination, in other words, bringing something from Earth to another world that we're visiting that we don't want to do. We don't want to discover life on another place only to discover it was us that brought it there. And then backwards.
Recently, that we brought it recently, right?
Yeah, recently, right. Yeah. Now, if it was a long time ago, then that would be interesting. So in any case, we have a big role to play in that, and those protocols that Janice was talking about in terms of how we'll handle these samples and how they will be used by the scientific community. So stay tuned for that. It's going to be great. I do want to just acknowledge we got lots of interesting answers from all of you about where you're watching from, and of course, all over the United States. So it's great to have our own friends here watching, including from Alaska and Hawaii, but we also had audience members from South Korea, and Brazil, India, Pakistan, the Philippines, Australia, of course, probably all related to Adrian, Malaysia, Puerto Rico, Serbia, Colombia, Chile, and Germany. And so amazing to have such a global audience, a planetary audience for tonight's event. So thank you very much for joining us. And again, of course, thanks very much to our speakers and panelists. And they will be receiving the highly coveted, extremely rare, these go for about $1 million on eBay. This is the SETI Talks mug that is, you know, the distinguished token of our appreciation to those people, those few people in that elite club who are guest speakers on our SETI Talk series. So that, together with the patch, will be forthcoming to all three of you. So thanks again very much. And I just want to also give an advance announcement to the September talk, which will be coming up on September 16th. And we hope you'll come back for that and bring your friends and family and let them know. But that's going to be a discussion about 2 upcoming European missions that are related to exoplanets. And of course, exoplanets are now this relatively new discovery that is pretty profound in its implications, that planets are in fact everywhere, and that there's likely tens of billions of planets in our own galaxy that are in the so-called habitable zone of their host star. So the so-called Ariel mission, which is Atmospheric Remote Sensing Exoplanet Large Survey. So this is a mission that's actually designed to probe the atmospheres of exoplanets with instrumentation of the kind that Janice and Adrian and Pablo have been talking about, where we can understand the composition of those atmospheres. Maybe there's biosignatures within those atmospheres that we can eke out. And then the CHEOPS mission, which is characterizing exoplanet satellite. So we'll be having guests with us for that event that'll be talking about those 2 exciting missions upcoming. So please plan on joining us on September 16th for that talk. And with that, I guess I'll bid our audience farewell and hope everybody stays safe, and that those of us here in the Bay Area don't melt, or, you know, worse. We'll try our best not to, but anyway, stay safe, stay well. Thank you for joining us tonight. Thanks again to our team at the SETI Institute, Rebecca and Lee and Jasmine, for pulling all this together, to Frank and Janice and Adrian and Pablo for being such a wonderful set of speakers tonight. Fascinating and great talk. So thanks so much. And with that, from Mountain View, sort of, California, and the SETI Institute, thanks very much, everybody, and good night.